in the past. Okay. And so yeah, it's great to be back. And I was wandering around the old town this morning and last night, and it was really great. So what I wanted to do today was to talk about frontiers in gamma ray astronomy. And this is something I've been involved with for about the last 4 or 5 years. I was doing management for about 10 years and I got fed up with that and then decided to go back to research. And so the area I've been focusing on is gamma ray bursts and what next in gamma ray bursts. And so I called this talk Frontiers in Gamma Ray Burst Astronomy. And just got one slide to kind of summarize gamma ray bursts. As you know, they're the most powerful explosions in the universe. And oh yeah, go ahead. Okay, great, thank you. So, as you know, these are the most powerful explosions in the universe. And there's been a huge amount of progress since they were discovered in 1973. And I'm going to kind of go through that very quickly, the history of what happened over the last 50 years of gamma ray bursts. And we now know that there's 2 sources for these events. One is massive stars that explode, probably type 1b or c supernovae, where they've had their outer atmosphere stripped. And a black hole is formed, and you end up with a jet coming out. When you view down that jet, you see the gamma ray burst. The jet is a relativistically powered jet. The more recent one that created a lot of excitement was gamma ray bursts from merging binary neutron stars, where you see a gravitational wave signal, and it's a big event, 2017, where you basically see a gravitational wave signal from the merging neutron stars. And again, you have a jet, and when you look down the jet, you see a gamma ray burst. And this really was a big event that sort of reawakened the interest in gamma ray bursts. It had been long predicted this would be the source of short gamma ray bursts, but it was confirmed, and a lot of stuff came out of it. So what I want to do is quickly go through the history of gamma ray bursts. And as I said, they were discovered 50 years ago in 1973. And in fact, they were actually discovered a few years before that. But it took a few years to figure out what was actually going on. And also it was discovered by satellites put up by the Department of Defense to do nuclear test ban treaty monitoring. And so it was sort of an unexpected serendipitous discovery. So the first, what I'm calling the 3 ages of gamma ray bursts. The first age was sort of the age of mystery. These GRBs were found. They're very brief events, very bright, very energetic, depending on exactly how far away they are. But they just last for a few seconds, and everyone was different, and they didn't repeat. And so it was very hard to figure out what they were. And so in their discovery, this sort of led to a large industry trying to figure this out. And probably this wasn't the only thing, but a lot of things in gamma ray astronomy were a mystery at that time. And it led to what was a great observatory that NASA launched called the Continuum Gamma Ray Observatory. And that did a lot of great work over 91 to 2000. It didn't really resolve the mystery, but it did show they were isotropical over the sky. It also showed there were 2 types, short and long bursts. And it was thought they were extragalactic, but there was still a lot of debate at the time about exactly what was the origin. Then there was what I would call the big breakthrough, which happened in 1997, and I'm sure you're all aware of this, with Beppo Sachs, Italian Dutch mission, that basically found afterglows. So through a quick, relatively quick at the time, hours, repointing of the spacecraft at the site of the gamma ray burst, an X-ray afterglow was discovered, and that's the picture there. And that lasted for hours to days, and it allowed arc-minute to arc-second positions, and then you could go out and look for counterparts. And that led to basically a new technique to locate and figure out what is going on with these things. And that led to the SWIFT, Neil Gehrels Swift Observatory, which was launched in, I think it was 2003. And that really opened up population studies of GRBs. SWIFT basically had a wide field of view gamma ray burst detector, but then and you had this redshift distribution. This is from a few years back, but you see you got GRBs going out to very high redshifts. So that was what I would call the second age. The first age was about locating them. Second age was following them up. So basically, even though SWIFT could find the X-ray and sometimes the optical counterpart, you basically need the ground to do all these redshift measurements. So what I'm calling the third age really happened in 2017. And this was the event I alluded to earlier. There was the gravitational wave event of emerging binary neutron star. And that event turned out to be very close by, relatively speaking. And it was coincident with the gamma ray bursts, short gamma ray bursts seen by Fermi and also integral. And this led to a huge slew of papers, thousands of papers for one event. And you know, a whole edifice being built on this one event, which turned out to be extremely rich, but also unusual. And we're still waiting really for the second event, and hopefully we'll get one soon as it goes back up and running again. But this is led to what I see as the third age, which is using GRBs as cosmic probes. So up until then, it's been more about GRBs intrinsic to themselves. You know, what are GRBs? How do they work? What's the physics of the jets? And so on and so forth. I think we're in a new era now where GRBs are really part of the whole astrophysics community structure and addressing broad questions in astrophysics. And I'm going to talk a little bit about that, as well as of intrinsic interest in their own right. So this is leading to what I would say future proposed missions. And I'm just picking the three current ones that are out there at the moment. There have been previous ones, and I don't be too long to go through all the previous history of this. But you're very familiar with Theseus, which Lorenzo was the PI on. There's a Japanese mission called Heisei Gundam, which has been around for a while. We think we may hear this week or next week whether JAX is going to proceed with it. And then the mission I proposed a couple of years ago to NASA called GAMOV. And these are what I would call third generation gamma ray burst missions. And they're really optimized to not only do gamma ray bursts, but also to use gamma ray bursts as astrophysical probes. And I'm not going to talk in detail about these missions. I will, if I have time at the end, talk a little bit about GAMOV. But what I really want to do is to make the point that we're in a new era of gamma ray bursts, and we need facilities to support that era. There's been a long history here, and we're basically we're looking for third generation observatories. So let me start with these two, what I see as the two frontiers. So the first frontier is a high redshift universe. As I showed on the previous chart, we're seeing gamma ray bursts out to redshift 8, 9. This is the same era now that James Webb is unveiling. This is a very important era. It's the era of reionization, when you have the Big Bang on the left, you have the current day on the right, and we have the CMB happening, recombination. That's called the Dark Ages, where you have just neutral hydrogen, the universe expanding. And then the first stars appearing, the first galaxies appearing, they turn on, they give off UV light, and they reionize the hydrogen. We think that's how hydrogen was reionized, but there's other possibilities, quasars, maybe X-ray binaries, maybe a lot of other different things, dark matter. It's a big mystery. How was it reionized? Are our theories about that correct? And how did that happen? You went from fully neutral to reionize the universe we have today. And then, of course, you get all galaxy formation and the whole evolution of the universe. But we are seeing gamma ray bursts from this period, and they are very useful probes. They're very bright for a few hours, maybe for a day or two, and you can use them as backlights. I mean, there's very, very bright light, just like a supernova sitting there. And if you get to them quick enough, you can just use them to get spectral fingerprints of what's between us and them. So that's the one frontier. The second frontier is emerging neutron stars. So as I said, we have one case now where it's been studied thoroughly, but this is just the tip of the iceberg. As things get more sensitive with LIGO and Virgo, and then there's a second generation of, maybe third, I don't know which generation they're in now, the gravitational wave detectors on the ground, but there's much more sensitive facilities coming in the 2030s and 40s. And we now know there's a connection between GRBs and these emerging neutron stars. We need facilities to be able to pursue those studies. So let me go back to this chart. I'll talk first about high redshift GRBs. Okay, and there's basically three questions here. There's probably more than three, but three which I'm going to focus on. I mean, first is how can we use GRBs to map the reionization history of the universe, and in particular the intergalactic medium. Then how do we use them to study chemical enrichment in the early universe? As I said, they're very bright backlights, and you see the fingerprints of the elements in those spectra. And the third is massive star formation at high redshift. So GRBs are caused by massive stars going supernova, creating black holes. If you measure the rate of these with redshift, that tells you something about massive star formation. So I'll go through each of these quickly. So as I showed earlier, one of the big achievements of SWIFT was measuring the redshift distribution of GRBs. This is like 150 GRBs. It's notable that at the moment you rely on the ground to get redshifts, and only about 30% of GRBs detected by SWIFT actually get followed up on the ground for one reason or another. Either it's cloudy at the observatories, or it's the wrong part of the sky, or whatever. But you only get about 30% of the redshift. So this is about 30% of the SWIFT GRBs. But as I said, reionization is happening in this period here. So we think it's probably around redshift 8 is the average. That's from the CMB observations with Planck. But the profile and exactly when this happened and what caused it is still a mystery. But GRBs are right smack in the middle of this. So what is reionization? As I mentioned at the beginning, it's basically caused by the formation. You're going through a period when there's nothing in the universe except hydrogen and helium. And then the fluctuations you see in the cosmic microwave background start to cause material to condense and collapse. Is that me?
No, it's the out of control.
Okay. And as this happens, stars form, galaxies form. You get these bubbles of ionized hydrogen regions around these stars, these galaxies, and they gradually start to overlap, and then eventually you get a fully visible universe. And as you know, hydrogen will absorb everything beyond the Lyman limit. And so, for the universe to be transparent, to see things, you really need reionization to happen. Now, there are actually many different approaches to measure reionization. James Webb is going to be doing a lot of work on that. There's some recent results that just came out. But just like when you're studying dark energy, you need multiple approaches to do this because every approach has its issues, its systematics, and GRBs are actually a particularly clean way of doing it. The only issue with GRBs is you've got to be fast because they fade. So, you've got to get there as quickly as you can. So this was the discovery from SWIFT and actually Subaru, the Japanese telescope in Hawaii, where the first high redshift GRB was found. And by high redshift, I mean above redshift 6. And this was a spectrum taken by Subaru about 3.5 days after the GRB. And it's already pretty ratty spectrum, three days, but it's still bright this is it's 8 meters, a Subaru telescope, I can't remember, but it's a fairly large telescope. And you can see here the damp Lyman alpha absorption line from hydrogen here. You can also see some oxygen lines and carbon lines from the galaxy itself. So you're seeing the intergalactic medium of the galaxy. You're seeing the IGM here, and you're also seeing some other Lyman beta from the IGM. So this is a really important result. I don't think it got enough play when it came out, because this really shows how easy it is to make this measurement. There's no complications. If you do a quasar, for example, you get all sorts of emission lines. The quasar has effects on this environment. So it's a very clean measurement. So just to talk a little bit more about this, so this shows you this damp Lyman alpha line. So there's two parts to this. One is this hydrogen in the galaxy itself, in the interstellar medium in the galaxy, which photons have to get through. And then there's the IGM around the galaxy, which you're trying to measure how much of that is neutral versus ionized hydrogen. And so, but they have very distinctive shapes. So this is the galaxy here, this red dotted line. And that red dotted line is just absorption in the galaxy, so it's at the redshift of the galaxy. Whereas the material that the IGM, the galactic medium between us and the galaxy, is coming at different redshifts. So you get a kind of a shoulder on the line. And this is for a redshift 8 galaxy and GRB, and for certain assumptions about how big the bubble is around the galaxy, the ionized bubble. So there's a bit of uncertainty here. And then the dashed line, dotted line, sorry, here is the combined of the two. So the trick here is you're trying to figure out how much absorption is in the galaxy, how much is caused by absorption in the IGM around the galaxy to measure the amount of ionized hydrogen around the galaxy. And you can see there's quite a distinct difference here. Now, as you go to lower redshifts, say redshift 6, where probably the galaxy dominates because the IGM is fully ionized, you'll see more of a shape like this. So there's a whole bunch of papers on this and how you do it. GRBs really, the sweet spot is when you get to the higher redshifts, because you're just dominated by the fact that the hydrogen is now neutral and you get a big damped Lyman alpha edge. And each GRB will be unique. So this shows you, so it's a confusogram, but this shows you with redshift versus the neutral fraction of hydrogen. All these cluster of points for current measurements, so GRBs are actually in there, the green ones. There's many different techniques. There's quasars, the orange ones, something called Lyman alpha emitter galaxies, which is blue points. There's many ways of doing this. The red lines here are predictions that was done by Adam Lids at Penn for what you would expect with a relatively modest number of GRBs with follow-up spectra from, say, the Keck or the VLT, what you would get for emission like Theseus or for Gamow. And you can see you get pretty nice error bars here for a relatively modest number. This is 25 GRBs. And his work shows that even for, say, 13 GRBs above redshift 5.5, you can get constraints. And the ones that really play hard into this are the ones at higher redshift around 8. These two lines here show you different models for reionization, what's called fast and slow. So the green dashed is slow reionization, the blue is fast, and probably the reality is somewhere in between. So this is kind of what we're aiming to do. This is the sort of our plot we would, get the New York Times result for, just like today, where we had the gravitational wave background from the radio pulsar observations. So there are many ways of doing this. I just want to compare it to quasars. This is not to be negative on doing this with quasars, but GRBs are just much better if you can get them. The first thing is that GRBs have featureless parallel spectrum. They're just a straight synchrotron spectrum. And so it's ideal for fitting the Lyman alpha absorption profile. You don't have to worry about anything else going on in the system except for the intrinsic absorption in the galaxy. For QSOs, it's very complex because you've got to worry about there's emission lines, and the QSO itself is just playing into this whole thing. Another thing is that GRBs typically are in low mass galaxies. I'll come back to that in a second. So they're tracing typical regions in the universe, the early universe. Quasars, by definition, are in high density environments, and they ionize the zone around the galaxy themselves, and that's playing into reionization, but it's a special place, whereas GRBs are tending to be more the more typical place in the high resolution universe. Another issue that you need to measure is if stars and galaxies are reionizing, the photons have to get out of the galaxy. So that absorption that we were measuring from GRBs is actually measuring the escape fraction from the galaxy of photons getting out to reionize. And we think this is around 5 to 10%, but it's a number we need to measure. And we actually get that direct measurement from the GRBs. And the last thing, which is probably the thing that's really exciting with GRBs, is that QSOs basically are just not there in the high redshift universe. They're starting to turn on maybe around redshift 7 or 8. I guess we're going to find out from James Webb exactly, and probably from Euclid, exactly when they turn on. But you're not expecting a huge number, and the current calculations are there's only really one quasar in the whole universe at redshift 9. So that's pretty hard to find that one, probably. So again, I want to emphasize multiple techniques are required here. There's other ways of doing this, 21 centimeter observations and so on and so forth. GRBs, I think, are a particularly important way to do this. I just wanted to mention that there's a recent paper that just came out on the preprint server about James Webb doing Lyman alpha damping wings, just basically in ordinary galaxies. This shows you some work done by Mader et al. You can go and look it up on the preprint server, where they basically measured all these galaxies. They're like 27, 28th magnitude, where you see the Lyman alpha break here, and they binned up. They've got like 26 galaxies, and they binned up with stacking in each of the bins, these redshifts, the spectra, this is the sum of many galaxies. And you can see this Lyman alpha edge, the damping wing, is becoming more pronounced. And they use that to actually measure reionization. And these red error bars, this is the plot I showed before. It's amazing, this is from their paper, and the one I showed before, which is this one, which is from our proposal, is almost identical. So it's great to see that we're all on the same page on this, but you can see their error bars, these red ones are huge. It's a great measurement. It's starting to at least show there is a period when we think this is happening is correct, but you can see they can't tell the difference between all these different models. And it's also very, very hard to do with just these galaxies that have been detected in this very faint magnitude. And it's worth noting that individual spectra, we do them a GRB spectrum with James Webb, even 2 to 3 days after the trigger, it's 100 to 1,000 times brighter than these galaxies that they're looking at here. So, we just have an intrinsic brightness advantage. Okay, so that's reionization. Chemical enrichment is another thing we can do with GRBs, again, because we have these nice clean spectra. This is some work done by Neil Tanbier at Leicester. So this shows you a GRB that was measured by VLT X shooter, not a sort of fairly faint one. That was, even with the VLT, it was pretty hard to do. You see the Lyman alpha break here, but you don't see any absorption lines. So Neil kind of just threw in some typical abundances, and doing it with the coming EELT at LISO is building. At the same time after the GRB, you just get a phenomenal spectrum and you get all these metal lines. Now you can do this with James Webb as well. And if you get there earlier, you can do it with 6 to 8 meter class telescopes, 6 to 10 meter class telescopes as well. And the important thing here is measuring metallicity. This shows you the current state of the art from Heinz, where you're measuring metallicity using quasars and also GRBs to do this. So the GRBs are in red, just measuring the depth of those lines. And you can see there is a trend to lower metallicities at high redshift, which is kind of what we expect. We did some simulations for our proposal, our gamma proposal, what you can do in the high redshift universe. So this is from 5 to 10. This is sort of 5 on this one. The scales are a bit different, so be careful what you're looking at. You can see you can, from our simulations, make pretty good measurements of metallicity out to very high redshifts and potentially much higher if we get GRBs above redshift of 10. And yes, just be careful with this clock. That's 10 to the minus 2 here. This is 10 to the minus 2 there, minus 3 so down here. So you're really filling in this area here on this, and really the origin of the first metals and how they came to be in the high redshift universe. So the third part of this is host galaxies and star formation. And these are swift GRBs that were found using Hubble. So the GRB happens, you get a position, then you go back and look at the galaxy after the GRB is over, and you find that GRBs are typically in these very ordinary, not very massive galaxies that are undergoing star formation. And these are probably galaxies that are very similar to what you're going to see in the high redshift universe. And so you turn this around and you say, well, we know that long GRBs are typically identified with type 1 BC or broad line supernovae, which usually means there's no hydrogen or helium left in the outer star. So you're basically tracing star formation with these GRBs. And the only issue comes down to the fact you're looking down the jet, and you have to worry about what's the jet opening angle, how many of population of supernovae you're actually seeing, what percentage, and how do you use that to track star formation. And because you're looking at the most massive stars, you're typically sampling the initial mass function of stars at the very high mass end, which is very relevant in the early universe where metallicity are low. So this is some work again derived from Swift, where basically there's a number of papers on this. I've just picked one by Perley et al. There's many other ones that preceded this that are basically just look at this top plot. This shows you redshift versus the star formation density with redshift. The red line is what we call the Maddow plot, which is derived from other techniques, typically UV luminosity of stars. And this shows you what we're getting from gamma ray bursts. And you can see that it does roughly track. It sort of peaks around redshift 2 for GRBs, 2 to 3, a little late, earlier than the regular star formation rate. So there's either a deficit here or an excess here. And we think this is due to metallicity effects. GRBs tend to favor low metallicity environments. And that's causing a deficit in the recent universe where you're seeing less GRBs. And this is some work done by Giancarlo Girlanda and Rubens Salvatierra, where they basically model GRB evolution. So these crosses here basically model them against using the same parameters as the star formation rate. And so the blue is the star formation rate, the Maddow plot, and this is sort of making a correction for that based on metallicity. So you only take stars below a certain metallicity for the star formation rate, and then you start to get a match with GRBs. And they can then compare that to the rates for supernova 1 BCs and supernova 1C broad line. And what they find is in the local universe, about 1% of these supernovae are producing GRBs. As you go to higher redshift, it actually goes up to about 7%. And that's probably due to metallicity effects, but there could be a lot of other things going on, such as maybe evolution in the luminosity function. And the really exciting possibility is that we can test things like whether the initial mass function is getting flatter as you go out to high redshift due to metallicity changes and mass changes in the stars, the early stars that form in the universe. Okay, so that's the one frontier. The second frontier is the one in multi-messenger, which all comes back to this event that was seen in 2017. We had a gravitational wave event, a merger of two binary neutron stars causing this gravitational wave signal. I'm sure you've seen this, and this shows you the Fermi result here, where you see a short gamma ray burst. There's about a 2-second delay between this and this. So this was an unusual event. It was a very relatively nearby galaxy, 40 megaparsecs. So it's a sort of a lower end of the GRB luminosity. This 2-second delay was interesting in the sense that on one side, it actually gives you a measurement of the speed of gravity because you're going over 40 megaparsecs. And the two signals arrive, the gravity waves and the electromagnetic signal arrive within 2 seconds. So that allows you to relative measurement. But there's also a delay of 2 seconds, which probably is reflecting the formation process of the black hole and the jet that comes out and how that process undergoes. And we really like to get more of these. And then it was identified with the Kilonova, and this was actually all predicted before the event happened. And so it was a real vindication of many years of work by many people. And this shows you the Kilonova, the function of time. It started out relatively blue and then went red, and this end of it is mostly due to radioactive decay of elements that were formed. The ones in yellow and here, yellow here, which are all the heavy elements, the lanthanide-rich elements like gold and platinum. And this confirms a long-held theory that this is where these elements came from. This is, again, one event. The question is, how do these elements then actually get spread out around the universe? These short GRBs typically happen well outside the galaxy because they're merging neutron stars and can typically moved away from the center of the galaxy. So there's a lot of questions about what's happening here. We need more events, basically. So this is just set the path for future requirements. So that brings us to the second cosmic probe, is merging neutron stars or merging compact objects. So there's many questions here you can ask. So one is, the sources of the heaviest elements. These are R-process elements. We've got one event so far, and we'd like to get a lot more. You can actually use these to measure the Hubble constant independent of the cosmic distance ladder. The cheap gravitational waves actually tell you the luminosity distance. It does have an angle dependence, viewing angle dependence with distance. If you have electromagnetic signal, you can say it's in that galaxy, whatever, 100 megaparsecs or 500 megaparsecs. It actually removes some of the degeneracy, and you can actually make a direct measurement of the Hubble constant without any cosmic distance ladder involved. So it's an independent measurement. And then the fact you've got these extreme cosmic distances where you're seeing photons coming from hundreds of megaparsecs, and you've got gravitational waves coming from the same distance. That's got a long lever arm, and so you're going to start testing theories about rents and variance and various other things. You can do this with these events, but you need more of them, and you need to identify where they're from. So this shows you a plot that was done by Adam Goldstein around the time of this 2017 event, and this shows you, so I'll let it play again. So this shows you all the soft gamma ray bursts going off that were seen between 2015 and 2017 by Fermi experiment on the GBM experiment on Fermi. So you can see all these events are going on, and it was only this one gravitational wave event that actually led to the identification of this short GRB, and all the rest were completely wasted. A few of them were seen by Swift, and we got accurate positions and could follow up that it was this elliptical galaxy or whatever. But by and large, most of these events are being wasted. And what we really want to do is to, whenever there's a gravitational wave event going off, we want to find the short gamma ray burst that was attached to it, especially for the ones that we're viewing down the jet. And this just shows you the issue we have with the gravitational wave observations, again, from this event. So the LIGO error circle in the sky was pretty huge. And when you combined it with Virgo, it got smaller. The error size from the Fermi GBM, which is just based on the different detector directions, was still many, many, many square degrees. And because this was relatively nearby, folks with optical telescopes actually could just go around looking at nearby galaxies in this error region and find the counterpart, which they did find. But we were lucky, this was close. When they're further away, it's going to be a much harder game to play. And ideally, there are a lot of ground-based telescopes being set up to do this, some wide survey telescopes, and I'm sure many will be successful. But as you go further away, it gets harder and harder. And as LIGO and Virgo come online, we're now in the 04 run, which started. There's 05 coming on, and the horizon is being pushed out to, they say, around 325 megaparsecs in 05, around the end of the decade. You might even be able to get to 500 megaparsecs when you're looking down the jet. That's when you get the maximum signal from the gravitational waves. You really want to bring every asset to do this. And The one way you can do it is just to go up. Every one of these GRBs in this plot here has an afterglow. And you can actually go after that with a wide field X-ray detector to find the afterglow, get an arm in a position, just like Swift does for gamma ray bursts, and tell the community, hey, it's in this arc minute area, now go look. And it makes life a lot easier for them to do that. And this plot here shows you for all the Swift, many Swift short gamma ray bursts have been rescaled to put them at 600 megaparsecs, so kind of the extreme of where LIGO, final LIGO or vibe run will be. And you can see if you can get a wide field X-ray telescope on, these are typical sensitivities for such a wide field telescope. If you get it on within 200 seconds, you're still going to detect these things. If you could actually get there within 60 to 100 seconds, you actually could get there when the event is happening, because they're talking about getting pre-merger events, and when they actually start to see the signal appearing. And you could point to be actually on the event when it's happening, or close to when it's happening. So one solution to this problem is to have a wide field of view X-ray telescope that's ready to point at the area of sky where a gravitational wave event is happening, and then look for the afterglow from the soft gamma ray burst. This will obviously pick the ones that tend to be more looking down the jet, but even that in itself tells you a lot of useful information about the geometry of the jet. So, and as these horizons move out, it actually becomes only gamma ray bursts that will be able to be seen as you get out to gigaparsecs, which is what's going to happen in the next generation Cosmic Explorer and Einstein telescopes. So we need gamma ray burst observatories that are tuned up to do this. Now, one last thing before I get to the mission requirements is that, so Swift was launched in 2003, 4, 5, and it had this unique capability that had never been flown before. It had this wide field of view, what's called the Burst Alert Telescope, which is looking for gamma ray bursts. It had an X-ray telescope and a UV telescope. So the X-ray telescope actually was an Italian contribution. It actually came from the Spectrum X Gamma mission, which actually went defunct and then reappeared later. But this telescope was lying around ready to go when Swift was being proposed, and so it's a major contribution from Italy. The UVOL was actually a copy of the XMM UV monitor. But these are all on a rapidly slewing spacecraft that can basically point anywhere on the sky within 100, 200 seconds. And that capability is what you need for gamma ray bursts. But it also has now turned out that that capability has opened up time domain astronomy and really opened up a new awareness in the community of what you can do with something like this. And what I've got here, this is a paper by Gehrels and Cannizzo, who are both unfortunately now passed away, but a very prescient paper in 2015 about the fact that you can do a lot of other stuff that is discovery stuff. So the black lines are gamma ray burst discoveries, but red lines are other time domain science. So first shock breakout that was observed in real time, just by chance. Galaxy mergers, a jet tidal disruption event, a very young supernova, a glitch in an anti-glitch in a magnetar, and so on and so forth. And there's now actually a long list. And Swift has now become known for its more known for its time domain astronomy today. It's making like 5 or 6 TOOs per day to respond to inputs from the community. Hey, there's something happening there. Go point at it. Go monitor this AGN, whatever. And the key here is that the driving capabilities of Swift came from GRB follow-up to go after the afterglows. And that capability has also enabled a ton of time domain astronomy. So whatever you do with a future gamma ray burst mission for free, you're going to get all this other stuff. And I think this is something we should not be lost on the community, especially the community that's not part of gamma ray burst aficionados. So going back to measuring gravitational wave events, so we have LIGO and Virgo and CAGRA online, and we're going to have the future Einstein telescope. And so what do you need to follow this up? So You basically need a wide field of view X-ray telescope with about 1,000 square degree field of view. You can also have on board instead of a UVOT telescope like on Swift. So you're basically replacing this XRT, which is only a very relatively small field of view, with a very wide field of view lobster eye X-ray telescope, which is 1,000 square degrees. You're replacing the UVOT with an infrared telescope that can provide you arc-second positions and also follow up on the Kilonova, as well as do high redshift GRBs. And you need a rapidly zooming spacecraft like Swift. So what do we need for a future GRB mission? What I'm calling a workhorse mission. You know, there's a lot of proposals out there for GRB small sats, CubeSats, which are great. You know, they're going to fill a niche, a gap, but they're not going to last for a long time. And they're also small. So what we need is a workhorse mission that is going to replace Swift and Fermi that has a lot of characteristics. So I've listed what my favorites are. I'm sure Lorenzo has his favorites, and I'm sure you all do. But you know, one thing you need is a wide field of view GRB detector extending out to the X-ray band. You need to get arc-minute locations over at least half the sky. So you're getting as many GRBs as possible with arc-minute positions. And these two can be done differently. You can either do it with a prompt emission or the afterglow, which is how Swift does it. You need an infrared telescope that can do photo-Z redshift, so you measure the redshift on board the spacecraft as opposed to waiting for the ground. You know, you've got a 30% efficiency going to the ground, which actually gets harder as you get a higher redshift. You have on board a relatively modest near-infrared telescope. You can do what's called photo-Z redshifts, where you're just looking at different filters for the photo-Z dropout and measure the redshift on board and tell the ground immediately, hey, this is a redshift 8 GRB. You need to go look at it. Point the keck at it. Point JWST at it. But you need a rapidly slewing spacecraft like Swift. You need rapid communications, real-time uplink and downlink, so you can command the spacecraft to point, or you can tell the ground immediately what's going on. And then you optimize the ground-based follow-up because you know you've got things like James Webb, you've got things like the ELTs coming, you've got the existing telescopes like Keck, and you want those to do your near IR spectroscopy for the high redshift GRBs. And last but not least, you want a long lifetime. You want something that goes for 10 years or more, like Swift has, like Fermi has. Because the gravitational wave detectors on the ground, you know, when they will come online, who knows? I mean, we've been waiting forever for this next run of LIGO, which just started. You know, the gap was much larger than people expected. You know, so you've got to have your observatories up there for a long time, so they're ready for when these ground-based facilities come online. So I'll just finish by talking about the mission that we put in a couple of years ago, called the Gamma Observatory. It has a lot of overlap with Theseus. I don't think I'll talk about Theseus because you have Lorenzo here, can do much better, and I'm sure you've heard about it already. But this was a proposal we teamed between George Washington University and JPL to do a sort of a Swift, but optimized for the high redshift universe and following up gravitational wave events. So we have basically what we call lobster eye X-ray telescopes. These are a new technology using X-ray optics that are based on the eye of a lobster that basically allows you to have a very, very wide field of view using what's called micropore optics. And these are very lightweight, and so it's very easy to put them on a relatively modest spacecraft. And then we have a photo-Z infrared telescope, which operates with 5 simultaneous bands to measure redshifts and also just follow up gravitational wave events. And it's on a rapidly slewing spacecraft, very similar to Swift. But we decided rather than put it in low Earth orbit, we would put it at the L2 point, where you basically have a much better environment for keeping the detectors cold on the infrared telescope and getting the whole sky available, basically. You don't have the Earth getting in the way. So we proposed it November 2021. We heard last summer it was not successful. There were actually a huge number of proposals went in. It's the first time we proposed it. Ones that did get through for a phase A study had all been through the process before. So we're currently reflecting on the feedback we got and deciding whether we might repropose this. The next opportunity would be 2026, so 3 years' time. But we're also watching what's happening with Theseus to see if that goes forward. That will also affect any decision to rebid. So the idea is this: you have a real-time continuous downlink that then sends photo Z position information and all you need for these telescopes, big telescopes on the ground, to respond. So the Keck, the GGC, and Magellan were all signed up to provide that follow-up. We would also hope to get Gemini and BLT as well, and maybe EELT. We also would use James Webb if we can't get it from these telescopes to get the follow-up spectra. And then, so we're trying to get this alert out, including a redshift, within 1,000 seconds to those telescopes so they can get on target. At the same time, we will be listening for events coming out of LIGO or Cagra, and within 200 seconds, we would repoint these wide field of view X-ray telescopes at that region of sky, 1,000 square degrees, to look for the afterglow from the gamma ray burst and to transmit that back to the ground as quickly as possible so that it can then be followed up by other telescopes. So it's actually a complete package, a multi-messenger package, if you like, where we're combining the ground and space to do one or two clearly defined physics experiments, in my mind, which is actually a different approach to what's usually done. And that was one of the reasons we were unsuccessful, because getting guaranteed support from these telescopes as part of a proposal that would fly 5 to 7 years before, when we need these telescopes, it's very hard to get solid commitments from these ground-based folks, which NASA did not like. So I think I will stop there. I have a lot more details on Gamov, but I think I've probably worn you out by now, and we are starting late. So here's my summary. In my view, we're in what I would call the third age of gamma ray bursts, where gamma ray bursts are integral to astrophysics frontiers, not just interesting objects in themselves. And there's at least two areas where we're at with these new frontiers. One is the high redshift universe, reionization, early metals, and stellar evolution, and merging compact objects, so binary neutron star mergers, maybe black hole neutron star mergers, black hole mergers, if there's any materials and systems, which gives you information on the origin of heavy elements, cosmology, fundamental physics. And at the same time, we would still be doing the bread and butter GRB physics, bringing new capabilities to do that. But this would be, a sideshow relative to this core stuff that's more general astrophysics interest. And in my view, we need what I would call a third generation workhorse mission in the 2030s, because Swift and Fermi are not going to last forever. Swift will probably re-enter early in the 2030s. Fermi can go longer, but something's going to break eventually. And at the moment, the Theseus mission led by Lorenzo, that's in the mix for the next ESA M-class selection, that's the current flag carrier, so we need to get behind that. And it encompasses most of the things that I talked about required for this third generation. And with that, I will stop.
Thank you very much. Thank you. So thank you again. So let's hope that one of these missions, next generation, will be selected at the end. In Bologna, we are also leading another mission in competition with Theseus, not myself, but of course, which is called Hayden. So let's hope that at least one of the two is selected. So there is room for questions. So any questions? Rumi? Grattella?
But Gamma, what is the X-ray range?
So these lobster eye optics work best at soft X-rays. So it's about 0.5 kilovolt to 2 to 3 kilovolts. It can be pushed up to about 10 keV, but the area is very low. So it's roughly 0.5 kilovolt to 2 kilovolts.
GRB.
So yeah, so it could be a flare star. It could be so we would do the maneuver and then look for the infrared counterpart